All right, Honors Physics, let's record and do this. So first of all, the force of friction, it's very simple. Dependent on the atomic structure of the two surfaces in contact, like try your two hands and rub them together. Okay, obviously the more pressure between them, the more normal force, the more friction there is, and the more heat. Okay, but the actual ratio of normal force pressing between the surfaces to friction force is depending on the structure themselves. So if you could try the experiment of pressing your hand against the table or your desk with the same amount of pressure, you'll see, oh yeah, actually the hand seems to be stickier on the table than it does on my other hand. Your hands are kind of greasy and they're actually fairly smooth. You have to press them together really hard to get some friction. Okay. So we express that in physics just with a coefficient of usually kinetic friction. It's not always necessary to specify if it's K for kinetic friction or S would be static friction. It's definitely kinetic in this case. But in the symbol, I'll go over it again. The symbol, to draw this symbol, you make a stick like you're doing a letter P, but then instead of a bubble for a P, you draw the letter U. And that's actually spelled M-U in Greek, but it sounds like mu. And so I'm gonna start saying mu 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 out of habit, like I'm a kitten or something, and that's what it sounds like. But I mean this special ratio fraction. You could consider it a percent, right? If half of the force of normal force of pressure is converted into the force of friction, then that's a 0.5 or a 1/2 coefficient. Okay. All right then, the inclined plane. So we have just a block this time, a dot, we can approximate it, maybe a person pulling a sled up the hill to go sledding this winter, or maybe we're just on the loading dock and we've got to get this thing up there, or we lost control and sliding down. Okay, so many different situations. In this case, we're going to do this special case where we have a velocity. Perfect. We have a constant velocity going down. Okay, and then we actually want to calculate. So given just that, we can use Newton's laws and calculate our coefficient of friction equals what? Okay, the coefficient, it's really nice with forces. We have newtons and newtons on each side, so the coefficient mu is just a ratio. It has no units. It's not even percent. Oh, we can write it as that, but it's not. It doesn't have kilos or seconds or anything. It's just a number. Okay, so what number does it have to be? Now, look, it's resting on a surface like that at an angle. Your friction force is at an angle. Your normal force is at an angle. Only gravity points straight down. Well, that's terrible. That's a ton of trig to do. Every vector, and there could be more vectors, right? If I had a person pulling up, then I'd have to add yet another vector at that same angle. So boo, boo, no. Let's not do that. Let's instead just tilt the axes. So the positive x-axis is the direction that it's going. The natural speed of this thing is going down the incline with a constant speed. So we'll make that the x direction. And y just has to be, for the same simplicity of our old math Cartesian coordinates, y just has to be perpendicular to that. Okay, and now, aside from gravity, we don't have any y forces, and we know from experience that things that roll or slide down an incline, they don't jump off the incline, and we break our problem if we smash through it. So it's actually really easy to say ay equals 0, and since I said constant velocity, what do I know about ax? Sure. It's also 0. Oh man. So this seems at first like a really simple physics problem. There's no acceleration, but be careful. Okay. I kind of want to zoom in. Oh, well, okay, not yet. Before I zoom in, try to draw this picture as best you can. I will do my own version very soon. there will be a component of gravity that's perpendicular to the incline, and its magnitude is mg cosine theta. Okay, because that's forming, I know that's way too small for people in class to see. And there'll be a component parallel to the incline, and its magnitude will be mg sine theta. That's what I'm going to do next. I'm going to blow that up. Yeah. No. This is this is why this gets its own day, and it's really weird. Okay. So I'm going to do my free body diagram where my box or sled or penguin or whatever it is a dot. And I'm going to draw a dashed line at an angle. Sorry, I can't hand out rulers this year. And that's going to be my x-axis. And minus x is way up there. Okay, I want some equation room off to the left here. So otherwise I would just do this the whole board. Okay, gravity points straight down, mg. Good old down. Okay. But, can you see this? Look at this big triangle right there. It's a right triangle. Okay. I need to split this gravity vector into components according to my new x-axis. So I'm going to make another right triangle right there. And this bottom angle here is going to be my same theta. We're going to try 37 degrees at the end. Work it out in symbols because it's actually shorter equations. Can you see that? Look as if it's hard to see at first that these are similar triangles. But if this is a piece of pizza and my 2.5-year-old son picks it up and throws it on the floor, of course he's going to flip it over first to get tomato sauce everywhere. So then splat. Oh yeah, there's the tip of the pizza is down there, and the right angle is still over here and over here. So it is a similar triangle. Same angles, same proportions, but it's flipped over. Okay? So, because that angle is at the bottom and mg is the hypotenuse, let's write it right there. Easier to see anyway. Okay? We do our old SOHCAHTOA business. The opposite side is this one. Opposite the angle is this sine. Yeah, we had to rotate our whole axis. What a mess. Okay? And if I've got vector addition, remember I have to do this vector plus that vector, nose to tail. So the other component of gravity points against the ramp, against the surface, and that's mg cosine theta, in magnitude at least. Okay, those two components would add together geometrically like vectors to give me back my original mg. So I can just reuse those two instead in all my equations. Okay, and since all my other forces point either parallel to the incline along x-axis or perpendicular to it along y, boom, I have it. Okay. Speaking of y, because ay equals 0, I immediately know that the magnitude of my normal force must also equal mg cosine theta. See that? Normal force points up, right? Whoops, I can't draw them the same length because I organized my drawing poorly. Normal force up, cosine component of gravity down, and they cancel out. They must because I have no acceleration. Sum of the force, if the acceleration in the y direction is 0, sum of the forces in the y direction has to be 0. Newton was pretty smart. He annoyed everyone with how smart he was. Okay. Fantastic. So we just need the x component. Sorry, I'm going to keep moving the page up. Give myself some space. Okay. So, the x component is going to be plus mg cosine theta, because that goes downhill. Mg sine theta, excuse me. In my brain, I keep writing the same thing over and over. Wonder how that happens. Mg sine theta. And then minus the force of friction. But see how force of friction is just mu times normal force, and I wrote right there what my normal force is. Okay, so I just do minus this mu, and we don't know what it is, that's what we're solving for. Mg cosine theta. And since I have acceleration, I divide the whole thing by little m. Sum of the forces, there's just two, and divide by m. Okay. This is actually a medium hard example, because if I wanted to make it really hard, and I'll do this one time on the test, this is the famous girl in a sled. So here's gravity, here's the friction on the sled, then the girl pulls up the incline also. So there's just a third component. Okay, it's not impossible. Some weird stuff happens with negative signs, but we'll go from there. Okay, well look, the m's cancel. The ax is 0, we said before. Can I, let's see. Oh, good. Almost done. I want to zoom in now and scroll down. No, don't do that. I gotta have 2 points. 2 fingers on the thing. Oh no, I push extend page some more. Okay, and I kept it pretty wide. Do that again. Okay. Yep. Okay. So 0 equals g sine theta. Oh, I forgot a g. Equals g sine theta minus mu g cosine theta. That's my acceleration equation. The g's will cancel too. And I end up with mu equals the sine of theta divided by the cosine of theta. Do you know what that is yet from trig class? Because the sine is the opposite over the hypotenuse and cosine is the adjacent over hypotenuse. That's just opposite over adjacent, which is tangent. So, and in fact, the only assumption I really made here was that ax equals 0. If I was sitting at rest, it would still have to be true. If I was moving up the incline at a constant speed, I think that would still have to be true, wouldn't it, Calvin? No, because friction would oppose the motion. So if I'm down the incline or at rest, Calvin's going to double check me. Anyway, tangent of theta. So if theta is 37 degrees, then my tangent should be approximately, what's that, 3/4, or 0.75. Okay, and on the test, fantastic. We got about 1 minute on my video. On the test, you'll often see something like 0.75, 0.5, 0.2, 0.8, Calvin was talking about. It'll be some nice ratio. It has to be between 1 and 0, realistically. But it'll be a fairly easy number to work with. Any questions before I have to pause? Okay.